Good evening, everybody, and welcome to tonight's Lancaster Psychology Research Showcase series. Tonight we've got Patrick May, and he's going to talk to us about harnessing auditory neuroscience for green energy production, which is very timely with the G7 summit and all of that going on. So I'm very much looking forward to hearing all about it. A few housekeeping points. The format is going to be a 30-minute talk followed by 30 minutes of Q&A. If there are any further technical glitches, please do bear with us and we'll get them sorted as quickly as we can. If you have any questions during the talk, please feel free to post them in the Q&A box at any point during the session. We're going to be screening the questions as they come in, and if you would also like to know the answer to one of the questions that comes in, just go ahead and give it a thumbs up. And then that will help us to prioritize the questions at the end. We're going to answer as many questions as we can in the second half, hopefully all of them, but I'll let you know if not. Hopefully we'll be able to get most of the answers to them. If you do want subtitles, then click the CC button, but please note that we have nothing to do with these subtitles. Sometimes they're a bit funny, so apologies if they are not completely accurate. So having said that, please enjoy the talk, and I'm very pleased to welcome Patrick.
So tonight's talk is going to be about this. For an apparently inexplicable reason, I shall be talking about three things tonight: ocean waves for green energy, the auditory system of the brain, and machine learning. And I shall do this without hesitation, repetition or deviation, and I have 30 minutes starting now. So what do these three things have in common? Well, let's start by the notion of green energy. As I'm sure we'll all agree, it's high time to start saving the planet with green energy sources. And indeed, the UK has a target enshrined in law to slash emissions of CO2 by 78% by 2035. And similarly, the EU is looking to slash emissions by 50% by 2030. Now, the traditional sources of green energy are considered to be sunlight, and wind. So we have sun energy and wind energy, and the development of these technologies has been ongoing for a number of decades. So we're quite far with those technologies. However, they have an inherent problem in that sun and wind are unpredictable. For example, if it's night, the sun doesn't shine. If it's cloudy, the sun doesn't shine. The wind doesn't always blow. But ocean waves, these are renewable, abundant, widely available around the clock, and they are more predictable than wind and solar energy, at least if you're standing on the shores of a large ocean like the Atlantic. So the question then is, if we want to complement sun and wind energy with solar and wind energy with ocean wave energy, how do we do it? How do we capture the energy of the ocean waves? So there are several ways of doing it, and I shall be talking tonight about the wave roller technology. So the wave roller is a device that converts ocean wave energy to electricity. So it's basically a panel that's hinged at a platform sitting at the bottom of the sea, and the back and forth movement of water driven by water surge, by waves, puts the wave roller panel into motion, and this motion can then be turned into electricity. It's intended to be deployed in near shore conditions, so between 300 meters and 2 kilometers from the shoreline, at depths of between 8 and 20 meters. And it could be it can be completely under the water surface, or it can, like in this illustration here, it can also be protruding from above the surface. This technology is being developed by a company called AW Energy, located in Helsinki, Finland, and these people are world leaders in wave energy technology. So here is then the wave roller for converting ocean waves into electricity. And the question now is, what does this have to do with the brain, with the auditory system in particular? So the story begins about 5 years ago over a pint on a boat, on a pub boat in Helsinki, Finland, specifically the Flying Dutch. I met my friend Christopher Ridgewell for a pint to talk about this and that and about work. And Christopher happens also to be the CEO of AW Energy. And as we were chatting, we realized that our interests might align professionally. So I was going on about the brain and how fantastically complex it is, and how it's lovely to build computer models of it. That's because I'm an auditory neuroscientist and also a computational neuroscientist. So it's my job to build computer simulations of the brain, which hopefully understand us how the system operates. So Chris is, of course, engaged in a different kind of problem, how to make the wave roller operational. He explained to me that the wave roller samples ocean waves at a specific location. So ocean waves are spread across the ocean in 2 dimensions. So they're really 2-dimensional waves. And the wave roller, which we can see in the figure here, it's in a single location, and it samples the waves at this one location. So it's in fact, the wave roller is sampling the 2-dimensional wave as a 1-dimensional wave. Something similar is going on in the brain, where sound waves are 3-dimensional pressure waves in air, and what the brain does is, through the ears, is to sample these 3-dimensional waves at a single location, the eardrum. So we have a compression of 2-dimensional waves into 1-dimensional waves with a wave roller, and 3-dimensional waves into 1-dimensional waves with hearing. Now, for the wave roller to operate efficiently, it requires good prediction of the height and time of the next wave. That's because if you know when the next wave is going to hit and at what height, you can position the panel at just the right angle to maximize the power output. So it's therefore very important to be able to predict accurately how the sea is going to behave in the next 30 seconds or so. Now, the auditory brain, on the other hand, then is specialized in predicting what the next sound will be. And this is something that I've addressed in my own research. So the auditory brain is specialized in dealing with 1-dimensional waves, but also in predicting what the sound world might be doing next. So as we were talking, Chris and I, on the Flying Dutch, we realized that indeed our interests do align, and it wasn't a great leap from this then to come to the realization that maybe we should pool our resources and perhaps think of a way of using the computer models that I've been developing of the auditory system to make that into an artificial neural network which can predict ocean waves, which can then be used in Chris's wave roller to predict incoming ocean waves. So this is how the project started. So I'll say a couple of words about what artificial neural networks are and what they can do before we start talking about the auditory system again. So an artificial neural network is a collection of units where each unit represents a neuron, and these are all simulated on a computer. So here we have an arbitrary collection of 16 arbitrary units. The units will be connected to each other, just like neurons in the brain. We'll come back to how these particular neurons are going to be connected. That's another issue. And each unit is specified by its level of activity. So this is usually a real number between 0 and 1. And the level of activity of each unit depends on the input it receives from the other units in the network. So what are these units, and what is this activity and all this input? It's all computer code which is simulated. The activity levels and the inputs, it's just a series of numbers. So there are no real neurons in sight anywhere. It's all happening on a computer. But because it sort of is constructed in a similar way as the real brain, it can do similar kinds of things, as we shall see. So how do we use these artificial neural networks to provide us with predictions of, say, ocean waves? So there are many ways of doing this, and the method that we decided to use was the so-called echo state networks. The problem then is to map the input signal to the output signal. The input signal are the ocean waves of the past, and let's see if I can get the pointer going. So we have the ocean wave going up and down here, and this then is the input signal. This is how the ocean is behaving in the immediate past, and we want to map this. We want to determine on the basis of this what the waves of the immediate future are going to do. So we have a mapping problem from the immediate past to the immediate future. So how do we do this? Well, we define an input unit and an output unit, where the input unit is an artificial neuron whose activity level represents the wave height, or the height of the level of the sea. And the output unit, and it does that for the immediate past, and the output unit represents the sea level in the immediate future. So now all we have to do is come up with an artificial neural network that will connect the input unit to the output unit so that when you feed in ocean waves, it will predict what they will do in the immediate future. So by the immediate future, we mean something between 20 seconds and 60 seconds. So let's see how we do this. So we take an artificial neural network, a collection of 16 that we started with, and we give it a random structure. So this means that we connect all the units to each other in a random way. Some units will be connected with each other, others will not, and the strengths of the connection will vary randomly between each pair. We then take our input unit and our output unit, and we connect the input unit to all the artificial neurons in the network, and we also connect each artificial neural network neuron to the output unit. Now, if there is a relationship between the immediate past and the immediate future, such that you can predict the immediate future just on the basis of the immediate past, if this holds, then it is almost guaranteed that there will exist an artificial neural network of some kind that is able to perform this mapping from the past to the future in the correct way, so that it does the prediction correctly. So many problems are not like that. You can't always predict the future from the past. But when it comes to so-called dynamical systems, which the ocean certainly is, we have good hope that, yes, that what's happening now depends on what happened in the past. So the question then is, how do we find the right structure of the artificial neural network to do this mapping from the past to the future? So how do we find the right connections between the units and the right number of units that will do this mapping correctly? This is a very difficult problem, and this is what machine learning is all about. It's finding the right artificial neural network that will do the job that you require it to do. Again, there are very many ways of doing this. You can, for example, arrange the units of the artificial neural network in several layers and then use various mathematical methods to figure out each connection. So all the connections are changed according to an algorithm, and you then end up with a correct mapping from the input to the output. This is, in crude terms, this is what deep learning is all about. So it's going into the neural network and it's changing all the connections one at a time until you get the right solution. So this is computationally very heavy. It takes a lot of computational power and it takes a lot of time. Now with the wave roller, we're hoping to produce a prediction algorithm that'll just work on your laptop, and it should be a cheap laptop at that. So we can't really use deep learning. We have to use something which is computationally not so heavy. So the solution then is to leave this artificial neural network completely alone, not touch it at all, but only change the output weights. And you can do that. There are mathematical ways of doing that, so that you can guarantee that during the so-called training phase, when you're training the network to do the prediction, you're showing it the output that it's supposed to replicate. You can find exactly the right weights that at least in the training session, it'll do the job perfectly. And this kind of system where you only train the output connections to the output unit, this is called an echo state network, invented by Jaeger and Haas in 2005, presented in their science paper. And the artificial neural network in the middle, which we don't touch, in their terms, it's called a dynamic reservoir. So you might now ask, where's the echo? What's the echo in the echo state network? So what happens is that when you have the input signal, it makes each unit react or represent the input signal in its own specific way. So it breaks down the input signal into a myriad different representations. And because all these units, or most of them, are connected with each other, if you then suddenly end the input signal, this activity in the reservoir, it'll keep going. So it's an echo of the past. It's an echo of the signal which you've just stopped. So that means that the output unit is looking at when you then connect the signal back on again, the output unit is looking at a dynamic reservoir which contains information about the input signal, not just 1 second ago, but 2 seconds ago, 3 seconds ago, 4 seconds ago. So it's got information about everything that was going on in the input signal going well into the past. So it can use the fact that there is this echo of the past present in the network. You can then use that to guarantee that you can get a good result. Right, so now that we've trained the network, and I'll show you in a minute an example, once we've trained it so that on the training data it does a good job, we can then connect the output unit to the input unit and stop feeding it outside signals at all. And now it'll start producing predictions all on its own, and it'll keep going basically forever until you switch it off. So those predictions, of course, will get worse over time, but they can be very good for short periods of time, so say up to 30 seconds, as we'll see in a moment. Okay, so how do we bring the auditory system into this picture? So let's take a very brief overview of the kinds of things that the auditory system can do. So sounds have, the main feature of sounds is that a sound will have a frequency, which we usually perceive as a pitch. So here we have a sound wave, which has a low frequency, so it oscillates up and down. So per time unit, it has a relatively few number of cycles, and we hear that as a low-pitched sound. Once you increase the frequency, so you increase the number of oscillations per time unit, the pitch starts to rise. And here we can play an even higher pitch sound. And of course, most sounds in the world are not pure tones like we just heard. They are mixtures of different frequencies. So for example, if we add together these three sound waves that we see here, we get a sound wave at the bottom here, which looks quite messy. And it sounds like this, so quite nice in fact. Well, if you like that sort of thing. The point is that it's quite messy, although the constituent signals are pure sinusoidals, so very neat signals, but when you add them together, you get something that looks quite messy. So the brain's trick is that it's able to look at an audio signal, a sound signal that is quite messy like this, and it's able to determine what different frequencies it contains. So where does it do this? Where is the machinery for figuring out what frequencies are contained in any sound? This happens in the ear. So let's have a quick look at the ear and just have a quick look at what it does. So we have here the earlobe, and we have the ear canal, which ends at the tympanic membrane, otherwise known as the eardrum. So what the eardrum does, it captures the sound wave. It starts vibrating in sync with the incoming sound wave. So it's a representation of the incoming sound. That's what the eardrum does. And these vibrations of the eardrum are then make this set of three small bones called the malleus, stapes, and incus. They start vibrating too, and their function in the middle ear is to amplify the vibrations of the eardrum. And this amplified signal then makes the oval window vibrate quite forcibly. The oval window separates the middle ear from the inner ear, and here we have the inner ear, which the main part of it is the cochlea, which is this snail-like structure filled with fluid. So when the oval window is vibrating, it's making pressure waves inside the fluid of the cochlea. And then these pressure waves, the cochlea can use those to analyze which frequencies are contained in the incoming sound. Now that whole process would require a whole 1 hour talk of its own, and it's quite fascinating, but I won't go into the details. But this information then, this breakdown of what different frequencies the sound is made of, is then fed into the auditory nerve in such a way that the auditory nerve contains a map of sound frequency. So depending on what frequencies are present in the sound, a specific set of nerve cells in the auditory nerve will become activated. So the activation of the auditory nerve, in terms of which cells are active, is a representation of all the frequencies that are present in the sound. So the auditory pathway starts at the cochlea and the auditory nerve, and then it makes its way up through the midbrain, through the cochlear nucleus and the midbrain and the thalamus, to the so-called auditory cortex. So the cortex is this large part of the brain, sort of the outer part of the brain, which is just underneath the skull, which is where most of our intelligent processes are happening, and also seeing and hearing is occurring in the cortex. So there's a special part of cortex which is dedicated just to analyzing sounds, and it's called the auditory cortex. So we have a pathway that starts at the cochlea, which is a frequency map, and then this information makes its way up to the auditory cortex. So importantly, at each stage of this auditory pathway, the frequency map of the sound, which is created by the cochlea and then passed on to the auditory nerve, this frequency map is maintained at all these relay stations on the way to the auditory cortex. That means that at each stage of the auditory pathways, some nerve cells become active when low frequencies are present and others when high frequencies are present. And you'll see the same principle operating all the way up in the auditory cortex. So let's have a look at what's going on in the auditory cortex. So what the auditory cortex does, it takes this frequency information that's coming from the cochlea originally, and then it duplicates it many times. So it produces lots of frequency maps that are all operating at the same time. And each frequency map in the auditory cortex is called a field, so that each field contains one low to high frequency map. So we can have a look at what this looks like in cortex. So this is now the surface of the cortex, and the color coding signifies the frequency, the sound frequency to which the neurons at that location are most sensitive to. So green means that they are sensitive to low frequencies, blue to mid frequencies, and red to high frequencies. And when you color the cortex, the surface of the cortex, you get this map of frequency with an archipelago-like map of frequency with islands of high frequencies in oceans of lower frequencies. And this is in fact the number of different fields, where each field is a single map containing the frequencies from low to high. Depending on which animal we're looking at, so for example in monkey there are going to be 13 different fields. We're not quite sure how many fields there are in the human auditory cortex, but there is research ongoing to try to figure this out. Okay, so that was a quick overview of the auditory system, the auditory pathway and the auditory cortex, and how frequency is represented. How do we then use all this information and pack it into our echo state network so that the echo state network perhaps starts to look a little bit like the auditory system? So what we do first is we take the input signal and we process it in a way which is reminiscent of what the cochlea does. So we take the input signal and we figure out which different frequencies the input signal is made up of. So we do a frequency analysis, so-called fast Fourier transform. And this creates a frequency map of the signal, which is something we do before we then feed this frequency signal, which is then coming into several different frequency channels. We then pump that into the dynamic reservoir. So that's step number one. Step number two is to design the reservoir so that it structurally mimics auditory cortex. We can do this because we have quite good structural maps, especially of the monkey auditory cortex and the rat auditory cortex. So we know the sort of structure these fields make up. So they are organized in a very hierarchical way. So that's quite easy to replicate or to copy in a computer simulation. And that's exactly what we do in this project. So we end up with multiple fields, each one containing a frequency map. There are some other details which I won't go into, but these are the two biggest innovations that we came up with to change your regular random network, echo state network, into a system that mimics the auditory system. So, in presto, oven ready, all ready to go. Let's see how this actually works. So here we have some actual wave data. We have time in seconds on the x-axis, and we have ocean surface height in meters here on the y-axis. We now define a point before which the data will be used for training the echo state network. So the actual training data is going to go further back in time, but we'll just show this bit here. And we're now going to train the echo state network on this data here. And that's now the output. This is what the output unit will give us. It'll follow the wave data exactly. And that's just a mathematical inevitability. We can train it during the training session so that it predicts with 100%, well, almost 100% correctness the data. What we then do is we switch off the input signal here, and we connect the output unit to the input unit so that it starts producing a prediction. So we now have, again, the wave data in blue and the echo state network output unit in green, and it does quite a good job, sort of up to 30 seconds. And then when we look further into time, the prediction becomes worse and worse, as one would expect. But for this initial period, it's doing quite a good job. So this is quite typical for an echo state network. Even the vanilla version, the random network version, usually does a good job, but it depends a little bit on the data. So in this case, we found that the auditory system echo state network always performed best. So I'll now show you, this is a slightly longer section of data where at the trough of each wave we retrain the system, which is something we would do with the wave roller too, because we're only interested 2 waves ahead, so we can always retrain as we go along. So the traditional echo state network is not doing such a good job. So we have in black this time the ocean wave data, and in red the prediction. Not so good. Now when we use the auditory system model as the reservoir, we get much better predictions, and these are about as good as you can hope to get. So to our delight, we found that this works. We are now in the process of publishing this, and this algorithm will indeed be useful for the wave roller, and it can be used on a cheap laptop rather than a high-powered computer. So in summary, ocean waves are a promising source of green energy, but ocean wave power plants need good predictions of incoming waves if they're going to be efficient in producing electricity. Nature has provided us with a system that specializes in dealing with wave signals, the auditory system of the brain. And we found that the computational principles of the auditory system can be harnessed for use in machine learning to serve green energy production. So that concludes the talk. I would like to thank my colleagues. We are an international bunch. My colleague in Germany, Reinhard König and Artur Matysiak, who's from Poland. And in Norway, we have Henrik Kalisch. And in France, also working in Norway, is Volker Röber. And I would also like to thank Christopher Ridgewell and Jussi Orkaberg at AW Energy in Finland, who made this whole project possible. And then, where did the money come from? All of this costs money because people need to get paid. So the European Commission provided us with funding. This is a 5-year project, which is coming to an end next year, part of the Horizon 2020 program. And this is what we look like. And then finally, as my going away present, just to convince you that, because so far I've shown you drawings of wave roller, not the real thing. So the real thing does exist. It's a prototype still, but it has been deployed outside Peniche in Portugal. and I'll show you a short video of the wave roller actually being deployed in Portugal. It will end with an animated bit which shows where we're heading towards. So it'll show you the bottom of the sea covered in wave rollers, all waving in unison and producing lots of electricity. So let's hope you enjoy this. Sorry for the abrupt ending, but there we are. Thank you very much indeed. Daphne, over to you.
That's fabulous. Thank you very much, Patrick. That was a really interesting talk, and very, very important at the moment, especially with the G7 summit and trying to find greener energy sources. It sounds really, really promising. We do have a question for you, Patrick.
Right.
Somebody who did not provide their name would like to know, can you use the wave roller to predict an upcoming tsunami?
No, you can't, because in fact what you need to predict is the cause of the tsunami, which can be an earthquake or it can be a landslide, and these are fiendishly difficult to predict. Well, I mean, we know, for example, that the western part of one of the Canary Islands will collapse into the sea. It could happen next year, it could happen in 100 years. It'll cause a 50-meter tsunami which will engulf the east coast of the US. We have no way of predicting when that's going to happen, but we know it will. So
scary stuff. Yeah, I was wondering about the materials that the wave roller was made from. Is it made from recyclable materials or recycled materials? Of what's kind of the life cycle of a wave roller? Is it something that's going to last a long time? Is it similar to kind of wind turbine, you know,
yes,
lifespan and that kind of?
Yes, so it has to be pretty robust because it gets sunk to the bottom of the sea and there it stays. So I don't think one uses recyclable materials. One uses whatever, you know, produces the best result. Again, this is not really my area, the actual sort of engineering aspects of it, but certainly sort of if we can get the predictions correct of or when the waves are coming in, that means that the forces on the wave roller will be smaller, and that'll mean that the lifetime of the wave roller will be extended considerably. So there, the prediction is also going to be helpful. I think we're well, I shouldn't really say. I wonder if Christopher Ridgewell is on the line. He might be. He'd be able to answer this question. But I think we're talking about several years, a bit like wind turbines, indeed. But the calculations have been made, and it makes economic sense to go ahead with this sort of thing.
Great, thank you. We have had a couple of other questions in. So Dina would like to know, she says, first of all, thank you very much, it's fascinating. She says, how do the two networks differ? Is it that the auditory work helped establish parameters of connectivity that transferred to the wave problem?
Yes, so so we have the traditional echo state network is just a random network. There's no structure to it at all. So what we've done is add structure, and that structure mimics the structure of the auditory cortex, and that we understand quite well. I mean, we still have lots of gaps. We're not 100% sure, especially with the human auditory cortex, but we have a sort of pretty good idea that there are lots of these frequency maps and that they are hierarchically organized. And that sort of organization, it's sort of dead simple to replicate that in a computer simulation.
So I suppose kind of the order of nature that doesn't seem to have any order, but that actually when you delve deeper into it, there does seem to be an order, both in terms of the auditory system and the waves, the ocean waves.
Yes. So that's actually one of the mysteries. Why are there so many duplicated frequency map in Cortex? So this is nature's solution to the problem of dealing with one-dimensional data, sound waves, and also making sense of them and predicting them. So the solution involves the use of several frequency maps. We don't understand how. We can see that it's happening, but we don't really understand what all these different fields are doing. The situation is different in the visual cortex. We have a much better understanding in the visual cortex. You find fields in the visual cortex too, and we have quite a good idea of the sort of things that they are analyzing, like color and motion and shape and position in space. When it comes to the auditory cortex, we don't really understand it very well at all. We don't know why there are these fields and what they're doing. So perhaps I'm hoping that this work might actually help us understand it. It's an intuitive idea at the moment. I'm sort of toying with it that perhaps if you have lots of copies that sort of slightly differ from each other, you can find interesting information in the differences if you structure the system properly. Perhaps something like that is going on. But again, one way to probe this is to build computer simulations of the system and then to see what we can learn from those and then test the ideas in the lab, hopefully.
Right. There is another question, but before that, I'd just like to kind of ask a follow-on from that. Did you expect that this would tell you more about the auditory system, or did you expect just to learn from the auditory system and apply that to the waves? Was it expected to be a kind of reciprocal thing?
Yeah, oh yes, in the end, yes. I mean, it's very difficult not to make progress in science when you start doing things. I mean, it's almost impossible. When you start fiddling around in a crazy project like this, it'll inevitably teach you something. You don't know what it's going to be, but chances are it's going to be useful also from an auditory neuroscience point of view. So again, I don't know what that lesson is yet, but I have a feeling that this will be quite valuable down the line.
I'm sure it was. I'm sure it will. It sounds amazing. We have a question from somebody who hasn't left their name. Say, how widely can the wave rollers be used, and is it applicable globally? Yes.
So it's possible to do quite sort of good mapping just to find out which coastlines are most suitable for this sort of technology, and most of the Atlantic sea coast, for example, and the Indian Ocean and the Pacific, so the large oceans are sort of ideal for this kind of technology. There are also places where it's not going to work, for example, the Baltic, which is strangely where Helsinki and AW Energy are located. The technology is not to be used in Finland. So yes, and there are ways of figuring out, before you actually deploy the thing, there are ways of figuring out where the most optimal place is going to be. So that's a science and an art of its own, in fact. There are people who are very good at doing that, and they are actually part of the consortium, the Horizon 2020 consortium, working on this problem.
Great. So do you expect this to take over kind of the wind turbines, to replace wind turbines, or to work in conjunction with, or different things for different places?
I think the idea that these different technologies are going to start complementing each other. So we're not going to get rid of solar energy. We're not going to get rid of wind energy. With ocean wave energy, it's just a more reliable source, and it'll work through the night, and it'll work even when there's no wind blowing. If you're standing at the Atlantic seaboard, you still get waves very often, even though you don't have wind. So yes, it's a very, very useful addition to what we already have. So every little bit helps.
That's great. Well, thanks again for coming tonight and talking to us. Oh, hold on. There is one more question just come in. Agatha wants to know, can you say why it can't be used in the Baltic Sea?
The waves just, okay, again, this is not really my area, but it's because the waves are just not powerful enough, is my guess. But again, I should really check that with people at AW Energy. But yes, you don't get the sort of large rolling waves you get in the Atlantic. So it's, I mean, looking out to sea from Helsinki, it could be a lake most days. So it resembles a lake rather than an ocean. So that's my answer to that question.
Thanks. That must be rather disappointing to be doing this and not be able to use it right on the doorstep when there's plenty of water, but just not enough waves, I suppose. Okay, well, that's all the questions for you, Patrick. Thanks again. And have you got the last slide for us that I can put up?
Oh, yes.
So thanks everybody who has come along tonight. I'm sorry about the technical glitches. Hopefully we'll take those out before we pop that on the YouTube channel. This was the last talk of this series. So thanks again for coming along tonight and for coming along to any of the other talks that you've been to. And thanks to all of the people who have given up their time to talk to us. If you would like to see any of the talks from before, then please head over to our website. Let me just pop that on the screen now. So you can find a link to this talk as well as all the other talks in this series and our previous series last year, our lockdown seminar series, at the Research Showcase series website, which is right there on the screen. You can also follow us on Instagram, Twitter, and YouTube. So thanks again, and we hope to see you again soon for a new series.